Hey guys, I am in the process, or I'm going to record for you a video of how you would solve one of the combustion problems, which are some of the ones you have assigned for this week. So I'm gonna, without further ado, I'm gonna share my screen and I'm gonna pull up a combustion problem that we can walk through. There we go. So here, I'm gonna read to you I'll get my little picture out of the way here so you can see better. Here is the worked out solution. I'm going to read you the problem and then we'll step through how you would solve a problem like this. Okay, so the problem says, this is actually review question 13 from your book. And the problem says you have a 200-gram sample of an unknown substance that's burned in oxygen and it produces 439.3 grams of CO2 and 239.9 grams of water. And it also says nothing else is produced. So those are our products in totality. And then they ask us, what's the empirical formula? Well, this is a long problem, which is why I'm walking through it for you. Here is the process by which we would solve that problem. Okay, for this particular problem, we have carbon and hydrogen and oxygen that are all in our original fuel. So here's the process. We're going to use the grams of carbon dioxide they gave us to figure out how many moles of carbon dioxide we produced. We're going to then take the moles of CO2 we produced and figure out how many moles that would represent in the original fuel. We'll do the same thing with the water. We'll take the grams of water that were produced and figure out how many moles of water were produced. Then we'll take the moles of water that were produced and we'll figure out how many moles that represented in the fuel of hydrogen in the fuel. And then, that's the first part of it. In earlier problems, that was all you needed because the particular fuel only had carbon and hydrogen. This fuel also has oxygen associated with it, or as part of the fuel. So we have to figure out, even though we haven't been given any information about oxygen alone, we have to figure out how many moles of oxygen are in the original fuel. Well, how are we going to do that? Well, if we can, because we have figured out the number of moles of carbon in the fuel, oops, sorry about that, the moles of carbon in the fuel and the moles of hydrogen in the fuel, what we can do is convert those into grams. So we'll figure out how many grams of carbon we had, how many moles of, how many grams of carbon we had, how many grams of hydrogen we had, and we do have the original mass of the fuel. So if we subtract the carbon and hydrogen that we calculated were in the fuel, what we'll have left is the grams of oxygen in the fuel, which will then convert to moles of oxygen in the fuel, and then we can compare ratios. I know that's a lot of information, we're going to step through it, but that's the process we're going to do to figure out the empirical formula, okay? So let's go ahead and scroll on down here. We'll jump into the first part of it. Okay, so we know from earlier problems we've done that the molar mass of carbon dioxide is 44.01 grams. Get my little annotation tool up here. We also know that the molar mass of water is 18.02 grams. So we're going to start with, again, this is the original amount of fuel were given. Oops, it's not very good, little check mark. The original amount of fuel we've been given, the original amount of carbon dioxide that was produced was 439.3 grams. So by using the molar mass of carbon dioxide, which is 44.01 grams, we can determine the number of moles of carbon dioxide we have in our product. Okay, this is the moles of CO2 as a product, 9.982 moles. Okay, the question is, how many moles of carbon do we have in the fuel? Well, we know, let me get rid of my annotation tool. We know, right, that CO2 has only one carbon in it. Oh, don't know what happened there. Only one carbon in it. So for every mole of CO2 in our product, we started with 1 mole of CO2 as a fuel. So if we had 9.982 moles of carbon dioxide as a product, that means we also had 9.982 moles of carbon as fuel. So that's our moles of carbon in our fuel. Let's scroll on down. Let's figure out the moles of water. Same thing. We have 239.9 grams of water in our product. We know the molar mass of water is 18.02. If we use just the molar mass ratio, we end up with 13.31 moles of water as a product. But what we're trying to find out is, how does that relate to the moles of hydrogen in the original fuel, right? Well, how do we know that? Well, we have to think about that. This is when we've talked about this. If there's 1 mole of water, every 1 mole of water has 2 hydrogens in it. The only place that those two hydrogens could have come from was the original fuel. So that means the original fuel has twice as many moles in it of hydrogen as the number of moles of water that we are producing. And that's what we're saying right here. Hydrogen has 2 H's in it. For every 1 mole of H2O in the product, we had to have 2 moles of hydrogen as a fuel. So that means, we multiply that, right? 2 moles of hydrogen over 1 mole of water. We had 26.62 moles of hydrogen in our original fuel. Okay, so now what we're going to do is convert those moles that we just figured out, right? 9.982 moles of carbon, 26.62 moles of hydrogen. How many grams does that represent? That represents, by using just the molar mass, 119.9 grams of carbon, 26.9 grams of hydrogen. Now again, why am I doing that? I'm doing that because I've got to figure out how much oxygen was in my fuel. So I started with 200.0 grams of fuel. I was told that. I know through all the calculations I've done that that represents 119.9 grams of carbon, 26.9 grams of hydrogen. So if I subtract both of those, what's left must be oxygen in my fuel. So that means I have 53.2 grams of oxygen in my fuel. Okay, we're getting there. One step at a time, guys. Okay, now what we're going to do is take those grams of oxygen that I just calculated, right, back up here. We said we have 53.2 grams of oxygen. So let's turn those into moles, okay? 53.2 grams of oxygen, 1 mole of just oxygen is 16.0 grams of oxygen. So in my fuel, I had to have 3.33 moles of oxygen. That's the amount of oxygen in my fuel. So again, let's look at these numbers all together. 26.2 moles of hydrogen, 9.982 moles of carbon, 3.33 moles of oxygen. To figure out my empirical formula, I'm just going to check the ratios of those, okay? I'm always going to divide by my smallest number, okay, which is the oxygen, 3.33 moles. So I take my 26.62 moles of hydrogen divided by 3.33. I get 7.99, which rounds to 8. And I have 9.982 moles of carbon divided by 3.33 moles of oxygen, which is 3.00. So what does that mean? That means for every 1 oxygen, scroll down here, I have 3 carbons right here and 8 H's. I would then list this as C3H8O. That is my empirical formula. So that's finding the empirical formula of this problem. Now, the second part of that problem, 13b, said, what would the molecular formula be if the molecular mass is 180.33 AMUs? Okay, how do we figure that out? Well, let's scroll down here a little bit. If the molecular mass is 180.33 AMUs, that means the molar mass had to be 180.33 grams. So if I take my molar mass, compare it to my empirical mass, then what I'm going to get is some ratio. Okay, let's go ahead and do that. So 1 mole, and at first I got to figure out the mass of my empirical formula, right? So that is C3H8O. So if I do the calculations for that, 3 times 12, 8 times 1, 1 times 16, I have an empirical mass of 60.11 grams. So now we're going to go ahead and compare the molar mass to the empirical mass. 180.33 grams divided by 60.11 grams gives us a ratio of 3. That means we multiply everything in the empirical formula by 3. What does that look like? C3 times 3, H8 times 3, O1 times 3. That would give me then a molecular formula of C9H24O3. And that, my friends, is how we solve this kind of a problem. I hope that is helpful. And I will see you back here for the next video.